press the bell icon on the YouTube app and never miss another update.
Now this is first PUC Physics Oscillation Part 2. Now in the previous class we have discussed about certain basic concepts of motion, like what is motion, what are the types of motion, translational, rotational, oscillational. And another important type of motion is, periodic motion. A motion that repeats again and again at a regular interval of time is called as periodic motion, and the time taken to complete one motion is called time period. It is constant for a given periodic motion and it is different for different periodic motions. For example, rotation of earth period 24 hours, revolution of earth around the sun period 365 days or 1 year, etc. Now a motion that executes to and fro motion or back and forth motion at a regular interval of time about a fixed point or position called mean position is called an oscillation motion or oscillatory motion or vibrational motion, So an oscillational and vibrational motion is a motion that repeats again and again at a regular interval of time, executing to and fro motion about a fixed point called mean position. The periodic and bounded motion of a particle about a fixed point called mean position is an oscillational motion or vibrational motion, And we have also discussed about some basic concepts like period, Period of oscillation or time period of oscillation is the time taken to complete one to and fro motion, Frequency of oscillation, it is the number of oscillations or cycles or to and fro motions completed in 1 second, Frequency may not be whole number, it may be fraction. Frequency is measured in hertz and time period is measured in second. We say that one oscillation or one vibration is one complete to and fro motion about the mean position, Now we will take up another concept, that is linear displacement. It is denoted by Y. We know that in oscillation the particle continuously changes its position with respect to time, with reference about the mean position while executing to and fro motion. The linear displacement of an oscillating particle at any instant of time is the distance of the particle from the mean position at that instant of time, The linear displacement y of a particle executing oscillation is at any instant of time is the distance of the particle at that instant of time, and it is denoted by the standard symbol, right, y, right. Now suppose let us consider a particle at O. It is the equilibrium position and mean position. It is vibrating along x direction or oscillating along x direction between the two extreme points, say m and n. When the time t is equal to 0, the particle is in the mean position. As the time passes, it moves from O to n, then from n to O, right? Now from O to m and m to O. That completes one oscillation, right? Now suppose while moving from O to n, let t be the position of the particle at any instant of time t. Then, right, the distance OP is called the linear displacement. Here, linear displacement, right, y is equal to OP at time t. Now as the motion continues, right, as the particle executes to and fro motion, the value of displacement changes with respect to time. So the value of y changes with time because the oscillating particle occupies different positions at different instants of time. Suppose if we take a simple pendulum oscillating about its mean position O. This is the mean position O at time t is equal to 0. As it moves, right, during the oscillation, suppose it occupies a position P at an instant of time t, then this linear distance between O and P, right, represents y, that is the linear displacement. Here linear displacement y is equal to OP at time t, because as time changes displacement changes. Therefore we say that the linear displacement of an oscillating particle at any instant of time is distance of the particle from the mean position at that instant of time, right? Is it clear? Sometimes the displacement may also represented by x, right? If it is represented by x, then the displacement OP is equal to x, right? Here if it is represented by x, then the displacement OP is equal to x. Generally we take y. We can also take the symbol x for displacement. We will discuss it right later now. Now, another important concept, it is amplitude of oscillation or amplitude of vibration. It is denoted by the standard symbol capital A. We know that an oscillating particle executes to and fro motion about the mean position. When it starts moving from its mean position, it cannot move indefinitely in one direction, right? It moves to extreme position, then it comes to rest momentarily. Imagine a simple pendulum, oscillating simple pendulum. Then it reverses its direction, starts moving towards the mean position. It won't stop at mean position. Then it overshoots the mean position and it moves away from the mean position on either side again to another extreme position, right? When the particle, right, reaches its extreme position, it is the maximum displacement. It cannot have a displacement beyond that extreme position. The maximum displacement of an oscillating particle, right, on either side of the mean position is called amplitude, right? Now, the maximum linear displacement of an oscillating particle right, from the mean position on either side of the mean position is called amplitude. Right? Suppose again we take a particle at mean position O. On either side it is executing to and fro motion with two extreme positions, say M and N. This is the position when time t is equal to 0, right? Now when it moves to a point P at a time t, and this is displacement, but the maximum displacement, right, is from O to N, right? It is denoted by plus A. Again it has a maximum displacement, right, from mean position on the opposite side, that is M. This is taken as a negative because these two extreme positions are on either side of the mean position. N is towards right of the mean position and N is towards right of the mean position and M is towards right the left of the mean position, right? Now when we take a simple pendulum with its mean position O, having two extreme positions, this is position N, this is O, this is position M. Now so this is minus A and this is plus A, right? So we know that linear displacement Y changes with time, but amplitude A is constant for given oscillation. For a given oscillation, amplitude is constant, right? And the condition is there, right? If there is no loss of energy of oscillating particle, maybe due to friction or any other oppositions, the amplitude remains constant. You see it here. Now, when time t is equal to 0, y is equal to 0. That means at time t is equal to 0, displacement y is equal to 0. As the time passes, at t is equal to t, displacement y is equal to OP from this equation, right? Now, at t is equal to t by 4. Here, if t is the period of oscillation, say t is equal to 4 seconds. While move from O to N, it takes 1 second, 1 by 4, t by 4. And again, from N to O, it takes further 1 second. Total time, 1 second plus 1 second, 2 seconds, t by 2. Again, from O to M, 1 second, 3, t by 4. Again, from M to M, 1 second. It is 4. Therefore, we say that the period is 4. So, here the time period is t by 4. Again, while coming back, it is t by 2. Here it is 3 t by 4. Again, it is t. Right. Now, at t is equal to t by 4, we see y is equal to plus a is equal to on. It is equal to on. Now, so I will take it here. At t is equal to t by 2. See here. While moving from O to N, displacement goes on, increases. After reaching the maximum value A, then with increase in time, the displacement decreases and it becomes 0, right? Now, y is equal to 0. Then, when t is 3t by 2, at t is equal to 3t by 4, now we see it here, it has minus a. Y is equal to minus a. When it again comes to O, at time t is equal to t, the displacement y is equal to 0. So, for one period of motion, right, now the displacement, right, changes from 0 to plus a to 0, again, right, it changes from 0 to minus a to 0. This is why we are saying that linear displacement changes with time, but amplitude remains constant. Amplitude is independent of time, right? A given oscillation has a constant amplitude and different oscillations will have different amplitude, right? Suppose, for example, while doing an experiment with simple pendulum, just it is any object like stone or a bob suspended by means of a thread. You can perform it. You put it in mean position. You just move 10 centimeter away from that mean position. Just exactly 10 centimeters. Then it began to oscillate. Right. Now exactly it moves, covers 10 centimeter towards mean position, then 10 centimeter towards extreme position N. Again it oscillates like that, right? 10 centimeter to right of mean position, 10 centimeter to left of mean position. If there is no loss of energy, amplitude remains the same. On the other hand, for the same simple pendulum, you pull it 15 centimeter, then you allow it to oscillate. Now the amplitude is 15 centimeter, right? If there is no loss of energy, the amplitude remains the same. There is no change in amplitude with time, but linear displacement changes with respect to time, right? That's all about the two important thing, linear displacement and amplitude. Now, we have another definition, that is angular displacement, that is theta. Generally, in any periodic motion, right, we can have two motions, one linear motion and another one is angular motion. See here, suppose a particle is executing, right, circular motion. So this is the center of the circle O, right. Let A be position of the particle at any instant of time t is equal to 0 then. Now as it moves, suppose the radius is equal to r. Now as it moves from A to B, B to C, C to D and D to E, right? And that completes one circular motion, one cycle in a time period t, right? This is t by 4, t by 2, 3t by 4 and this is t. See here, when I take the case of the second handle of the needle, when it comes 12 position to 3, it has covered an angle 90 degree. The tip travels to certain distance, at the same time it covers angle. When I take 12 to 12, one rotation or one circular motion, the distance covered is equal to circumference of the circle, but the angle covered is 360 degree, right? Now how we say that? Now when it comes to the position B, obviously we say that, right, the radius vector, we say call it as, right, now OA is the radius vector we call at position A, right. When it comes to a position P, now the radius vector shifts its position from OA to OP. The radius vector shifts its position from OA to OP. Its magnitude remains the same here, right? So OA is equal to OP is equal to radius. But here the radius vector here, it describes some angle when the particle executing circular motion moves from position A to position P. Here we say that when it moves from position A to position P, circular motion, there are two displacements here. The position of the particle, right, can be expressed in two ways, right? See here. Now the position of the particle AT, right, is called linear displacement. It is measured in meter. Both linear displacement and amplitude are measured in meter, right? But here angle POA is called angular displacement. It is denoted by theta. Generally, any periodic motion we can take is associated with two motions. One is linear motion and another one is angular motion, right? Similarly, when a particle is moving along a straight line, that is linear motion or translator motion, we have some terms: displacement, speed, velocity, acceleration, momentum, etc. Right here, all these quantities, right, are called linear quantities: linear displacement, linear velocity, linear acceleration, linear momentum. Right? We know that velocity is the time rate of change of displacement. Acceleration is the time rate of change of velocity, and momentum is the product of mass and velocity. At the same time, the motion is also expressed in terms of angle theta. Here we have angular displacement, correspondingly angular displacement means angular velocity, angular acceleration, right? Angular momentum, etc. Even when we study the rotational motion, we come across two quantities: linear quantities and angular quantities. Generally, in the three types of motion, right? Translatory motion, rotatory motion, and oscillatory motion. The two, oscillation or oscillatory motion and oscillatory or oscillational motion, are periodic motions. But translational motion is not a periodic motion, right? When you are sitting in a car and moving from one place to another, you are executing translatory motion. You will not retrace the same path while coming back, right, in opposite direction, right? But when you are sitting in a joint wheel, you retrace the same path again and again. From top to top you go, you have two displacement. One, linear displacement, right? That is, the total distance traveled is equal to 2 pi r, circumference. And also you have angular displacement, right? That is equal to 360 degree or 2 pi, right? So here, since oscillation is a periodic motion, here the motion is analyzed in terms of linear quantities due to linear motion and angular quantities due to the angular displacement, right? So don't worry, don't get confused. We are discussing oscillation, that is to and fro motion about mean position, and I have taken an example of a circular motion, right? Motion of a particle along a circular path with constant radius with uniform speed is called uniform circular motion. You will discuss the thing under motion in a plane, right? But there is a close relation between this circular motion and oscillation. Generally, in further, right, next classes or so, right, we are expressing oscillation in terms of circular motion, right? That's why at this stage I have written it here, right? So AP is linear displacement, but angle POA is equal to theta is called angular displacement. Suppose if I take a simple pendulum. Here, when it is its mean position, time t is equal to 0, angular displacement theta is equal to 0. Say the simple pendulum during its motion, it comes to a position t at an instant of time t. Now, the string, right, through which the bob of simple pendulum is suspended, the string moves from, say, this is position O, this is position P, and this is position some A. It moves from the position AO to AP. Here, bob is executing linear motion, but the string, it is executing right angular motion. That is, it describes an angle theta. Right? Say this is the position AO and this is the position AP. Now here the string, right, get displaced through an angle theta, and this is called right angular displacement theta at time t. Again, angular displacement, like linear displacement, it changes with respect to time. So here, this distance is called y, linear displacement. You see it here. OP is the linear displacement of the bob at time t. But angle OAP is the angular displacement of the right string, that is the simple harmonic motion or the bob executing simple harmonic motion at the time t. Right? Is that clear? So, right, the angle described by an oscillating particle at any instant of time from its mean position is called angular displacement. Displacement theta. So, when time t is equal to 0, angular displacement is 0. When it reaches the point B, angular displacement is 90 degree or pi by 2. Here 180 degree or pi. Here 3 pi by 4. Sorry, 3 pi by 2. That is 270 degree, and it is 2 pi or 360 degree. Later we will discuss the relation between oscillation and the circular motion. Right? Again here linear displacement changes with respect, just like linear displacement, angular displacement theta changes with respect to time. Here the linear displacement y, corresponding linear velocity, linear acceleration and linear momentum are called linear quantities, right? And angular displacement, angular velocity, angular acceleration, angular momentum are called angular quantities, right? So, we will express this displacement or oscillation can be studied both in terms of linear quantities and angular quantities, and in later classes we will find the relation between linear quantities and the angular quantities. is, right. So this is angular displacement, right. Now another term we take, angular velocity, denoted by the symbol omega, right. Now here in motion in one dimension, we have detailedly discussed about velocity, linear velocity, the rate of change of linear displacement, and even in the next classes we will take linear velocity and linear acceleration. At this stage I am taking angular, right, velocity, right. Now angular velocity is defined as the time rate of change of angular displacement. Just like linear velocity or velocity is defined as the time rate of change of displacement. Here angular velocity of a particle executing in general periodic motion, right, is the time rate of change of angular displacement, right. That means, right, mathematically angular displacement, right, is equal to, right, this is, sorry, angular velocity is equal to angular displacement by time taken, right. Now suppose, let us consider a particle executing circular motion. This is O A at time t is equal to 0, the position. Now it moves to a position P at any instant of time t, right, describing an angle theta called angular displacement. When the particle is moving from A to P, right, it covers angle with respect to time. This rate of change of angular displacement with respect to time is called angular velocity. Therefore, angular velocity, right, omega is equal to theta by t. angular velocity omega is equal to theta by t, and generally it is represented like this. Omega we take in anti-clockwise direction. Generally when we are having circular motion, right, it may be in clockwise direction or in anti-clockwise direction. For simplicity or convenience sake, we generally take a particle executing circular motion in anti-clockwise direction. The reason is the angular quantities in anti-clockwise directions are taken as positive. Generally we see the angle is measured between the two lines OA and OP, and when we take clockwise direction, all angular quantities become negative. So in clockwise direction theta is positive, anti-clockwise direction theta is positive, and in clockwise direction it is negative. This is the reason why whenever we are considering a circular motion, we take the particle is moving in anti-clockwise direction. So all angular quantities are positive if the particle is moving in anti-clockwise direction, right? Now here the SI unit of angular velocity is radian per second, and its symbol is like that because the SI unit of angular displacement is radian, and of course it may be expressed in degree. Generally angles are expressed in degrees. There is hexadecimal system like 0 degree, 30 degree, 60 degree, 90 degree, 180 degree, and in SI system angle is measured in radians, right? 0 radian, pi by 2, pi by 3, pi by 4, pi, 3 pi by 2, 2 pi, 3 pi, etc. Right? But the SI unit is radian per second. Right? Is that clear? Now, we are taking another point here. Note, number 1, we have angular velocity omega is equal to theta by t. We will take it as equation number 1. Now, for one revolution, when the particle moves from A along the circular path and returns to A, right? Again the position. Now for one complete revolution, right, that angular displacement theta is equal to 2 pi radian, or it is in degree 360 degree. Now the time taken t is equal to, so when it completes one circular path, the time taken is equal to time period, that is t, the time period. Therefore we have angular velocity omega is equal to, replacing this theta by 2 pi and replacing small t by t, right? This is equation 2. So this gives the relation between angular frequency and the time period, relation between. Now, but we have relation between frequency and time period. F is equal to 1 by t. Therefore, angular velocity is also given in terms of omega is equal to 2 pi, right? Replacing that 1 by t by f, 2 pi f. This is equation 3. So, angular velocity is expressed in 3 forms of equation. Omega is equal to theta by t in general, omega t is equal to 2 pi by t, and omega is equal to 2 pi f. Since this omega can be expressed in terms of frequency, this quantity omega or 2 pi f is also called angular frequency. Is also called angular frequency. Here, this term omega or 2 pi f is also called as angular frequency, right? So, both angular frequency and angular velocity represent the same physical quantity and their unit are radian per second. You see it here. Frequency, the unit is of frequency is hertz. Actually, hertz is per second. That per second is called as hertz. Therefore, unit of 2 pi is radian. Unit of frequency is per second. It is radian per second. And you have to remember in periodic motion, that is in rotatory motion or circular motion or oscillation, right? We use this term angular velocity, and angular velocity omega is equal to theta by t. Angular velocity omega is equal to 2 pi f. Angular velocity also called angular frequency omega is equal to 2 pi f. They are the very important relations in the study of oscillation, right? Now, we will take another important concept, that is harmonic motion. So, this oscillation is associated with angular displacement theta. And we have trigonometric functions like sin theta, cos theta, tan theta, etc. When we study this sin theta, cos theta, tan theta, etc., trigonometric functions or trigonometric ratios and how their value change with angle. For example, I will say sin 0 is equal to 0, sin 90 is equal to 1 plus 1, sin 180 is equal to 0, right. Now sin 270 is equal to minus 1, sin 360 degree is equal to 0. So we have sin 0 is equal to 0, sin 90 degree is equal to plus 1, sin 180 degree is equal to 0, sin 270 degree is equal to minus 1 and sin 360 degree is equal to 0. This is 0, pi by 2, pi, 3 pi by 2 and 2 pi. You see, when the angle changes for an interval of time 1 period, right, the angle changes 0 to 2 pi. Again, this continues for 3 pi, 4 pi, 5 pi, etc. Now, even when we take cos theta also, but cos 0 is equal to 1, right, cos 90 degree is equal to 0, right. Similarly, this cos theta also varies between plus 1 and minus 1. Both sin theta, that is sine function, and cosine function have bounded values, right. Now over a period of 2 pi, they can take the values between plus 1 and minus 1, right. So this sine function, that is sin theta, cosine function cos theta, are periodic, that is their period in terms of angle is 2 pi, right. Now and bounded. Now they have one extreme value of plus 1 and even sin theta also, it varies from plus 1 and minus 1, right, or we better to take plus 1 to minus 1, right, the two values, or if we take plus 1 is maximum, one extreme, and the minus 1 is minimum, that is one extreme. So among all trigonometric functions, only two functions, sine function and cosine function, are periodic functions and bounded. What is an oscillation, right? A periodic and bounded motion of a particle about its mean position is called, right, an oscillation. See, the oscillation of a particle, displacement we take, linear displacement, right, even we can also take the angular displacement. When time t is equal to 0, y is equal to 0, and at one extreme position y is equal to plus 1, and at another extreme position y is plus a, amplitude y is equal to minus a. See it here, we have 0 0 0 plus 1 minus 1, again y, even we take this one, oscillation O, this is M, this is N, this is plus A, minus A, 0, right, this is Y at any instant of time. You see, when time t is equal to 0, y is equal to 0. And now it can take a maximum value in one direction, plus 1. The next value, 0. The next it can take minus 1, that is minus a, and again 0. Over a period of 0 to 2 pi, both sin theta and cos theta can take the values minus 1, 0, plus 1. Here, over a period or angular displacement of 0 to 2 pi, right, the linear displacement can take the value 0, plus 1, 0, plus a, 0, minus a, again 0. Therefore, right, the oscillational motion, right, can be expressed in terms of sine function and cos function, right. Now, since sine function and cos function are periodic and bounded, we take the tan theta, right, is not bounded, we cannot take this one, that tan 0 is equal to 0, tan 45 degree is equal to 1, and tan 90 degree is equal to infinity, right. So here these functions are called harmonic functions or harmonics. So among the trigonometric functions, only two functions, cos theta and sin theta, are periodic functions over a period of 0 to 2 pi. They have bounded values, plus 1 to minus 1, right, and these functions are called harmonic functions or simply harmonics. Why only sine function and cos function are called harmonic functions? Because they are periodic and bounded. Once again, it as theta increases beyond 2 pi, the same value will be repeated, 0, plus 1, minus 1, 0, etc. Therefore, only sine function and cos function are called, again I am repeating, harmonic functions. What is a harmonic function? A function which is a periodic and bounded values, right, is called harmonics. Therefore, oscillation is expressed in terms of sine function and cos function. Remember here, right, oscillation is expressed in terms of harmonic functions such as sine function and cosine function, the sine theta and cos theta, right. Therefore, right, oscillation is called, right, harmonic motion or harmonic motion or oscillation motion is called harmonic motion. Is it clear? Why oscillation motion and of course vibrational motion are called harmonic motions? Because oscillation or vibrational motion can be expressed in terms of, right, sine function and cos function, which are, right, called harmonic functions, right? Therefore oscillation motion is called harmonic motion. For example, I say that we will derive that one in the next classes. This is y is equal to a sine theta or a sine omega t. Now x is equal to, again where x is displacement. I told you now while discussing linear displacement can be represented by the symbol y as well as the symbol x, right? We will discuss it later, under which condition we can take it as x, under which other condition we can take it as y. Now this is a cos theta, that is equal to a sin omega t, right? Now any motion, right, which can be expressed in terms of, right, sine function and cos function is called, right, a harmonic motion. Here oscillation can be expressed in terms of what? That sine function and cos function. Therefore oscillational motion and vibrational motion are called harmonic motion. Is it clear? Right. Now, another important concept, it is simple harmonic motion, abbreviated as SHM. SHM means, right, simple harmonic motion. Now we see that before going to this simple harmonic motion, we have two more things to understand, right? We take this as note point. It is clear that oscillation or vibration or is called harmonic motion. Why? We have discussed earlier. Second point is that now one we have oscillation and another we have vibration. So there is no much significant difference between oscillation and vibration. There is no much difference. You see, generally when we are representing in a harmonic motion. Depending upon its frequency, we call oscillation and vibration, right? Now here, harmonic motion of low frequency is called oscillation. Right. Harmonic motion of low frequency is called, right, oscillation. For example, oscillation of simple pendulum. We don't say it is vibration. Now, oscillation of loaded spring. So, when we have a simple pendulum, nothing, any object suspended by means of a thread and allowed to, right, oscillate, it becomes a simple pendulum. When we observe simple pendulum, we can see that the bob or object or particle in mean position, reaching extreme position, again reaching mean position also. When we have a loaded spring, we can also see the motion of that oscillating spring, because the time period is large and the frequency is less. Hardly it is right, one oscillation, two oscillation, three oscillation per second, right, like that. Frequency is very low. Now the third point, right, now harmonic motion of high frequency is called vibration. Generally, if the frequency is very high, 100, 200, 1000, right, 5000, and even in kilohertz and megahertz, right, then the harmonic motion is called vibration, right. For example, we say that vibration of a tuning fork. When we have a tuning fork, right, it is set into vibration by hitting against a smooth object, right. That tuning fork executes harmonic motion, to and fro motion periodically about its mean position. But we can't see the prong of the tuning fork reaching the mean position, reaching the extreme position clearly, because the frequency is very high that we cannot able to, right, observe that motion, oscillational motion. It appears as if the prongs are at rest. It is because of the persistence of vision. I can identify only 16 different changes in 1 second. If it exceeds more than 16 changes in 1 second, the eye cannot able to identify. For example, when we are seeing a movie, right, now 16 frames of that picture is passing through the lens in 1 second. If it less, the motion of the picture, that is motion of the object in the film, that becomes slow motion. If it exceeds 16, it becomes fast forward, like that. Say, so the harmonic motion of tuning fork is generally not called oscillation, it is called vibration because of high frequency. And again we are having vibration of strings of musical instruments. You might have seen and heard a musician, right, playing a musical instrument, stringed instrument such as guitar, veena, violin, etc. When a guitarist is playing a guitar or playing a veena, some other musician, we can hardly observe the vibrations in the string, right? We cannot clearly see the motion of the string as we observe the motion of a simple pendulum or a loaded spring, right? Therefore, it is called vibration. The remaining thing is same. All the things, whether it is linear displacement, whether it is angular displacement, whether it is amplitude, linear velocity, all the terms. Here also oscillation is expressed in terms of y is equal to a sin omega t. Right? In vibration also it is expressed in terms of y is equal to a sin omega t. All the concepts are same, but only the difference is the frequency. Right? Harmonic motion of low frequency generally called oscillation. Harmonic motion of high frequency generally called a vibrational motion. Is that clear? So, there is no confusion between oscillational motion and vibrational motion. The only difference is, right, one is harmonic motion of low frequency and the other is harmonic motion of high frequency. Both are harmonic motion. The concepts are very much, not very much, it is same, right? Concepts are same for both oscillation and vibration. Is that clear? Generally we say that while discussing heat and thermodynamics, thermal energy, etc. When we consider a solid, the particles of the solids, atoms or molecules, are always in a state of vibration. We don't say that they are always in a state of oscillation. They are always in a state of vibration because they execute harmonic motion, that is to and motion about mean position, with a very, very high frequency. Now, another important thing, right? Here we have discussed translational motion, little bit definition only, rotational motion, periodic motion. After discussing periodic motion, we come to oscillation, right, or vibration, because oscillation and vibration are basically periodic motions, but they are bounded, right? Therefore, here periodic and bounded motion about mean position are called oscillation or vibration or harmonic motion. Here, one thing is to be remembered is all periodic motions are not harmonics, right? All periodic motions are not harmonics, but all harmonic motions are periodic. Right. So all harmonic motions are periodic motions. This has to be remembered, right? All periodic motions are not harmonic motions, but all harmonic motions are periodic motions, right? For example, we take, right, rotation of Earth is periodic, but not harmonic. It has no mean position. It is not a bounded motion, right? But it is a periodic motion, right? Now, revolution of Earth or spinning top, right? And the motion of a person in a giant wheel, all are periodic but not harmonic, right? But we take motion of simple pendulum. It is oscillational motion, therefore, right, this is harmonic. And also it has a period, it is periodic. So all harmonic motions like oscillation, vibration, oscillation of a pendulum, right, now oscillation of a loaded spring, vibration of a string, vibration atom, all are periodic. They take a definite intervals of time to complete one motion. But all periodic motions are not harmonic motions. Is that clear? Now, we are going to complete this class, right, at this stage. I think you have understood the basic concept, right, behind the terms what we have discussed, right. Mainly we have discussed linear displacement, angular displacement, amplitude, angular displacement, angular velocity, harmonic motions, right. In the next class, that is in part 3, we are going to discuss simple harmonic motion, because oscillation of a simple pendulum, oscillation of a loaded spring, etc., they come under, right, the category of simple harmonic motion, that is HHM, right. So far we have discussed what is a harmonic motion. Now we have required to understand what is a simple harmonic motion, right. Is that clear? Okay, we will continue in the next class, that is in part 3 of oscillation.